Hello, everyone. My name is Xuan. Welcome to join us tonight. So I just want to give you guys a very brief introduction about what particle physics is, like some background knowledge about like what has happening shown in the movie, and just like and also some fun demonstration. Also, a heads up: the front row audience might get involuntarily participate in some demo in case you want to like reconsider relocation. You'll see, but it's gonna be fun. And so, yeah, I will try to stay as brief as possible to not stand in the way from this like awesome movie. But just want to give everyone like a quick introduction about what particle physics is. Oh, wait, it's this way. Yeah, so what is particle physics? Like we're in this theater and we're in this cinema, like we breathe the air, we touch the seat, everything is made out of something. But what is made out from? Like, in the 1900s, people I just always realize it's this way. In the 1900s, people realized, all the elements that actually define a periodic table that contain all the elements that made the world around us. But what's in that element? And then we realized this in the late 1800s and 1900s that, there's actually a nuclei and electron operating around the nuclei. But is this the smallest? Nope, because we realized there's something inside the, there's something inside the nuclei, which is the quarks. But is there anything inside the quarks? We don't know yet. What we know is up until now, the best model to explain the fundamental particle is the standard model of elementary particle. So it has the two main components, the fermions and the bosons. You can see the fermions are like the building blocks then create our, like, the world we lived in. Like we have the quarks, up and down quarks to make the proton neutron to create the nuclei. And we have the electron orbiting around the nuclei to create create the atom. And also they have the three different groups. You can see the top and strange and charm and strange and top and bottom quark are just like the cousins for the top and down, and they only exist in the early universe and also the high energy, the laboratory setting. But they have very similar characteristic as the top and down quark, up and down quark. And on the top of, and also like on the bottom then we have the neutrino. Neutrino is kind of like a new particle we recently found out and we still don't fully understand yet. They're just like the reason why we haven't seen them, we really found them recently, is there's an antisocial kind of group of particle in the particle family. And while we're speaking, there's like billions of neutrino pass through your body and you don't feel it. So the thing is, so these are the first section of the standard model particle. The standard model. And then we have the bosons. They're the force carriers. So as far as we know, we have four fundamental forces in our universe. We have the strong force, and they glue the quarks together to create the proton and neutrons. And we have the electromagnetic force. Also, the gluon is a carrier for the strong force. And we have the electromagnetic force that is carried by the photons, the light, to like the thing mostly familiar with, the radios and other stuff, are from the electromagnetic force. And we also have the weak force that was carried by the Z boson, W boson, that is mainly from the nuclear reaction. And then we have the gravity. We haven't yet to find any carriers for the like gravity yet, but this is also one of the fundamental force. And then on the top, the very last piece of the standard model is a Higgs boson. It's also the main star of our movie tonight. And it is this is the original all the mass. So without the Higgs boson, we should all exist in this form and the energy. You can imagine like, so the early universe, like, you might heard the famous like E equal to mc squared formula from Einstein. And the thing is like, the reason why we are on the M side, not the E side, is because of Higgs boson. I'm trying to think about what would be the easiest way to understand how the Higgs boson work. I'm just imagining the Higgs boson is like the melted caramel. And you drop the caramel in without the caramel, you just get a bowl of granola. And then, but you drop the caramel in, it's just like everything is in the floating energy stage. But then when you drop the caramel, and then you get a protein bar, and that's the mass. And that's why that's the best analogy I can come up with. But the idea is the Higgs boson, it converts energy to mass. And so the particle physics it's not just about the space we're living in now, but also can tell us the history and the future of the universe. Because at the beginning of the universe, we think it's happened the Big Bang, and then it expanding to and slowly cooler down to where we are now. One of the aspect for the collider physics, we're trying to recreate the condition in the early universe stage to understand how the universe evolved and how it's gonna go. And so, how do we do it? Okay. Oh wait, so yeah, sorry, missed one. So the standard model is a beautiful theory that has explained a lot of natural phenomena in a very precise way. However, there's still things that we don't know. For example, like we have the dark matter and dark energy. We know that exists. So all of us, like all the things we touch on the stars, the galaxy, they're only 5% of the universe. There's still 90% of energy that we can observe. We know they're there by the experimental proof, but we haven't interacted with them yet. What are they? Why can we see them? And that hasn't been included by the standard model yet. And also, as I mentioned before, all the other fundamental force has their own carriers. What about the gravity? Like, is there a gravity that exists? We don't know yet. And also, another thing is, the universe loves symmetry. Like every part has their equal counterpart. We believe at the beginning of the universe, there's an equal number of matter and antimatter. But as we all know now, we exist in the stage of matters. Why did it happen? Why there's an imbalance of the brokenness symmetry? Where did the antimatter go? What has happened? And also on the top of that, neutrino is like such an interesting particle. Like theoretically speaking, they shouldn't have mass. And they also like changing their flavor. They're not like, they kind of like changing their type. Like for example, for a quark, if you're an up quark, you might decay to some other format of quark. But for neutrino, they change their flavor constantly. It's just like they decide their flavor type by day, it's just like changing clothes. And also mathematically calculate based on mathematical calculation, we don't have any reason to, it shouldn't supposed to have mass, but based on the experiments, we know they have the mass. So there's still many questions that we don't know about our universe, and it couldn't explain by the standard model. So we need to find a way to prove, to understand, to probe then the stage that was the universe that we lived in. So how do we probe it? Okay. We use the collider. So to study the smallest particle, we use the largest machine that is possible. So the Large Hadron Collider is located at CERN, Switzerland. It actually it crossed the border between Switzerland and France. So I think the border is somewhere here. And it has a 27 kilometers circumference, and the tunnels are all buried like 100 meters underground to prevent radiation. So people are still like there's farm on the ground. And then in the bottom, we have the largest, most powerful particle collider. And this is Geneva Airport to show us a reference. And then how things are work in the Large Hadron Collider. I would like to invite my students, Timo and Iwan, to show a demonstration.
Do we need hazmat suits?
You'll be fine.
Depends on how far you are away.
So if I can borrow one of the ball. What we were accelerating is this particle, pretend it's a proton to enlarge maximum. It has 3 quarks in there. The natural phenomenon, all the interesting particle and interesting event happens, so the thing is we just want to know what's inside. So we act like a crazy baby, an angry baby, we just smash things together. But the thing is just smashing, the difference between us and babies, we actually know what we're looking for. And based on the mathematical prediction, we know that when the particles, the little bouncy balls inside, hit each other, that's when the interesting event happens. That's how we create interesting particles. But there is a chance, like I will show, what happens if we only threw 2 together. The small balls not necessarily hit each other. So we can go through the collection, but nothing happened. So the way how we do in the Large Hadron Collider is we threw a lot of them together. So what we call the bunch. Each of the bunch has 100 billion protons in there. And the idea is like if you throw them, many of them enough, like they will, eventually some will hit. So if you guys want demonstrating how we look like in our Large Hadron Collider. And then that happened over and over again. Thank you. Yeah, this kind of events happen 40 million times per second in the Large Hadron Collider. And thank you so much for the demo. So, yeah, so the idea is like we threw a lot of particles, 100 billion of them, at the rate of like 25 nanoseconds, which is 40 million times per second. And they gave us a chance to find an interesting particle. But what left us? As you can see on the stage, a mess. Like, see, how are we going to dig out any information out of this? Like you see, it's scattering all over the stage. And the difference between a real particle and the bouncy balls is once the bouncy ball hits the ground, it still stays as a bouncy ball. But when the particle, especially the interest particles, they decay, they turn into other format particles, then we need to really be able to catch them at the really fast rates for us to be able to have a hint about what has happened. And also, another thing I want to point out is that we are looking for the bouncy balls, but there's the shells, there's all the other things around. So how do you tell what's going on in there? My favorite analogy for what happened in the particle collider is like you take your puppy to a park. And you are trying to figure out what the heck it ate the day before by going through what it pooped out the next day. You just have to sort through all the stuff and to be able to find a clue. And how do we sort through the whole mass? And therefore, we need another large machine called, that's the experiment we're working on and building, the compact muon solenoid. We're a very compact detector, which only 14,000 tons in the weight and 5 stories tall. And as you might already see many of this, like a picture of our detector in many of the pop movie. I definitely saw it in the Spider into the Multiverse and the Three Body and like a bunch of different other movies. And this is how it works. But when it's actually collision happening, these two parts actually connect to each other. And why do we need such big machine to study such tiny particle? Just say when the particle collide, it actually traveled into nearly the speed of light. With the energy of the Large Hadron Collider, the speed of the particle traveled to only 7 miles per hour slower than the speed of light. So therefore, everything traveled fast, everything happened like we need something large enough to be able to have a chance to capture what's going on. And also because of the mass you showed earlier, we need to find a way to sort it through. So there are different part of component of the detector just taking care of different kind of particle. First, like the part what Cornell mostly involved in is the silicon tracker, which this is in charge for record any charged particle. So regardless what kind of charged particle you are, as long as you have a charge, it will be recorded by the tracker. And then we have this electromagnetic calorimeter and anything like, but this cannot record things like a photon, like the light. So we have the electromagnetic calorimeter to capture the energy of the photons and the electrons. And then we have the hadronic calorimeter to record some like what we call the hadrons, like is for example proton, neutron. They're all kind of hadron. And then we have a big solenoid to bend the track. Why do we care about the bending? Because the curves give us very important information about the energy of the particle. And so we need a big 4 Tesla magnet to help us to go through, like to help us to study the energy. And also outside of that, there we have this like a muon system that help us to specifically study the particle. Muon is like a heavier kind of electron. And because they're much heavier, so it has the ability to travel much further, which can give us a way better signal to identify some interesting particle. Okay, let's see if I can get this going. Yeah, so that leads us to discovery. So sorry, I'm the worst speaker to give a talk before the movie because I give you the spoiler before the movie even happened. But spoiler, we found the Higgs boson. And as you might see, like those plots like in the movie. And so I just want to kind of explain the basic idea how we are doing the discovery. So like I said, many of the interesting particles then decay so fast, and our first layer detector is extremely close to the glacier beam, but they could just decay away before we even have a chance to take a look. So when the two protons hit together, there's some like reaction happen between different particles and create a Higgs. And then the particular discovery, the channel we're looking for the one mentioned in the movie, is the Higgs decays to two top quarks, and then they decay away to two photons. And then when we look at our events, and after we sort through all the trash and all the events that we're not interested, we found events that has two clear beam of photons. And then we say, okay, this is the signal we're looking. But the issue is we can only identify the final stage of what happened in the detector. We don't know if those are from the Higgs or some other thing. So we do some systematic calculation. And this is a plot that you will see they will emphasize a lot in the movie. And I particularly block out the mass bar in case anybody don't know the mass, because that's one of the like mystery in the movie to see where they are. But the idea is like, we want to know, like we know there's, okay, this is event that fit the description of Higgs, but is it Higgs or is it something else? So we go through all the mathematical calculation. What we do is, you see this like a green line is all the other possibilities, so all the particles that can turn into this kind of final stage. And this one is a combined, so this one has a better like a view of the different kind of, we think all the like photon can come from either Higgs or probably two like a Z boson. And we saw through all the other possibility, and then we fit our data and say, oh, wait a second, there's still extra data left. And they accumulate at this particular mass region. And once this like difference is large enough, which in our field we call it phi sigma, it means systematically significant enough, then we know, okay, this is a discovery, which means that it's like 99.9999% that is a Higgs boson. And so you will hear more about the particular discovery of Higgs boson in the movie, but this is just the idea. So why all particle physicists are like mosquito, we're so excited about bumps. And that's why we're excited about the bumps. And I also want to take this as an opportunity to acknowledge and honor the founder of the Higgs mechanism, the physicist Peter Higgs. Like, it is really give us a wonderful explanation about how the universe works and why it works in the way how it works. And the particle physics field wouldn't exist without his contribution. And he's such a wonderful human being. Like, we were all gonna deeply miss it. So we want to also use this opportunity to celebrate his like achievement in his life and how he brought to us for us to carry on to the future. So for particularly, I want to point out how we, Cornell, is working on building the future. So we are working on, like I mentioned there, we are working on different projects, both from the aspect of hardware and also like management and the physics analysis. So the thing we particularly working on in terms of building the detector is the tracker, which sits right at the center of the Large Hadron Collider. The center of the CMS, compact muon solenoid. So even though our detector is such a giant monster, like 14,000 tons, but the size of our detector is literally the size of shoebox. However, we're the heart of the CMS, and there's no way we can, like, there's no single phase analysis can live without our detector. And so particularly at CMS, we're building the inner, what we call the D. It's like the end cap of the pixel detector. And so we're working on the structure, construction, like you see this, there's some common fiber, like supporting structures hold the module, and these are the detector module. Even though they are like super tiny in the size, but they're extremely powerful. They're with the size of probably like a chip, like a old movie ticket. It has the ability to produce so many, like, I was thinking 2,000 gigabytes data per second, but that's not the way we got keeping because there's not enough, like, hard disk can store all the data. It can also make simultaneous decision to cut down the data to a more smaller rate to select through, to throw away any of the non-interesting mass and we don't care about. But also, we need to building a thing to put them on to support them to make sure them all sit together, and also to be able to cool them down. And we use robotic machine to hold on to constructing the D, and this is one of the gantry in the lab. And also, this is a picture of a student trying to install a real module for the D to demonstrating. As you can see, he has a weird ESD safe band because the detector is so sensitive, the static charge around our body will be strong enough to fry the module. So we have to constantly ground ourselves to discharge ourselves to protect the safety of the module. And while I was preparing for this talk, I found an interesting video online that to show what we are going to do in a few years. This is a video that was taken from the last generation detector, is the one currently running in the Large Hadron Collider, in the CMS. And I actually working on many of the production of this module when I was a student. But this is, it just gives you a scale about where we are compared with this like large machine. So you can see all the cables and all the modules, all the entire modules are here. And they're sitting on the cables. This is a video to show people when we were trying to install our detector to the CMS. You can see the kind of amount of precise work. We're like the heart surgeon for the CMS. You can see the size of the detector compared with we need to, I also want to emphasize how close, how tight the space is. Even though people are joking when we say we're compact, but we're really compact. And I think there will be one to the show. And this is a beam line where the collision gonna happen. You see, there's no room for us to like have anything to move around. And that's a close look. And the funny thing is, like, this part of the end cap of the detector was all built in the US. And so we did not, how do we send it to CERN? We don't trust the FedEx to handle such $1 million delicate machine. So we bought a flight ticket to make our technician take them on the flight. They have their own document, their own passport to go to CERN and to install them. But yeah, I thought this is a fun video to show where we are, what we are building. And Cornell is building the next generation of this detector. And this is exactly what we're gonna do like in a couple years. And also, the other project that we're working on is the track trigger. So there's, like I said, there's so many data happening. There's so many events happening. And if you're gonna store all the data, there's no way we can store, like we're gonna run out of the disk space in the whole world. So we also need some fast decision trigger system to work. So Cornell team is also working on the FPGA design, which is a hardware trigger to design what data to keep, what to throw away, and also how to reconstruct. Because you see there's a proton, there's like a photon and stuff, but that's already after some level construction. What we actually see in the detector is just like the hit of dots in different layer. We need to connect the dot to figure out what particle we're looking at. Because like, there's so many different ways to connect in the dot. You can connect this way, you can connect this way. How do we know which one we should connect them and how we connect them? So there, we're building this hardware to make a decision based on the distance between each of the hits and based on their spatial location and the information of the other timing, and to find a quick way to to help us making this kind of decision. Okay, and this is a picture of to show the size, and this is my colleague holding the FEC board to show the relative size. And they will sit outside the experimental hall and on the shelf like this, and this is all the different kind of board we're producing. So we build the instrument, but we also, important thing is use the data we're taking, the instrument we built to take the data to do the physics. So after the Higgs boson, what are we looking for? And there are so many remaining mystery in the universe. We need to figure out a way to untangle them one by one. I want to highlight some of the research we're doing as Cornell. I'm trying to make them all together, but if different groups are looking for different signal. So for example, I'm personally working for the search for looking for dark photon. We're trying to see if we can produce dark matter inside the CMS for us to have a good look at it. And so we're looking for signals that has two leptons, like this case is muon, and some thing we think that might be a dark matter goes through that way, and this is some events we see in the detector to have the potential to be the dark matter. And there's also, we know there's a way to produce the Higgs boson, but is there any other way to produce Higgs boson? There's another search in the green is to look for if it's possible to produce, measure the production rate of the Higgs boson with some other like 2 top quarks. And also we're looking for some other particles, and because also a lot of interesting particles, they have very short lifetime. Is there any interesting particle that has a long lifetime? And the blue ones, they're looking for that kind of signature to see how many, like, if there's any new particle fit in that description. So we're doing a lot of different search in CMS to understand, like, our universe. However, I also want to point out that the particle physics is more than just the, like, collider physics. So, for example, at Cornell, we have a dedicated team working on this experiment called G-2, and they're studying the interesting feature of the muons. And also, I saw a couple of my favorite, like, other experiments. For example, one of my favorite ones is ice cube. Like, people are trying to find neutrino, which they can come from the universe. Like I said, billions of them come through your body. So what do? They realize the water in the South Pole is so pure. So just melt the ice and put electronics into the water, and they use the ice in the South Pole as their sensor to detect the particles. So it's like a free, like, large detector for free. And also, like, we're looking for dark matter. We possibly create them in the collider, but if we see any, how do we know it is a dark matter? And so there are experiments like the Super CDMS and the Dark Energy Survey to directly detect the dark matter and dark energy in the universe to prove that we can cross-check to make sure that whatever we see was indeed the dark matter. And also, I saw this is also a fun picture to show. I just saw that in the 3D body problem on Netflix. And this is a neutrino detector called the T2K. It's in Japan. They literally have the people sit in a boat inside the detector. I don't know if you can see this, like, rough boat inside to clean their electronics. So yeah, there's a lot of exciting things happening around the world. But also I want to bring the attention to us locally. So I think not that many universities can say we have our own particle accelerator, but we can. So CLASSE, the Cornell Laboratory for Accelerator-based Sciences and Education, we have our own synchrotron that sit right under the football field. I think you can see this, you might see this, like, brown building, then it's by the football field, and there's a little tiny brown building on this side, and we are the Cornell synchrotron accelerator, high energy synchrotron, is sitting right underneath of this. So it's called the CHASS, the Cornell High Energy Synchrotron Source. It's now it used to have the similar purpose as the Large Hadron Collider to study the particle physics, but now we're using this as an amazing X-ray source. And there are different, like, study has been done in the synchrotron lab. For example, people from biology can send their, like, plant sample to look up at how the, like, virus invading through the plant. And there's also, like, I think during COVID, there's some pharmaceutical company who was working with us to study the, like possible solution and, like, a vaccine for combating COVID. And also there's a different kind of search done, like, for example, we have a large team study on the superconducting superconducting magnet for the accelerator, because, like, I emphasize a lot on what we do on the detector, but we do need a lot of study on how to make the accelerator to be more powerful and stronger. So that's a lot of work. And also, I think this is a fun thing. We have one of the things is a storage ring inside the accelerator. And why do we need storage ring? Because the synchrotron we have is an electron and positron accelerator, but because positron is like the antimatter for the electron, the issue with antimatter is they decay super quickly. But we wanted to be able to use them. How do we do? And I don't know if you guys are familiar with relativity, and so if you run faster, your time gonna go slower. So you can use the accelerator to keep running to delay the time it can for us to have time to use them. And it's sort of funny to say, why do we need a storage ring for our particles? But classes, we do a lot of amazing science class, but one thing I want to point out tonight is that's not class. This is CLASSE. CLASSE is made by over 200 employees and working all different kind of area of the field. People might always, and one thing I think it's important to say is physics is not just about physicists. Because if you look at the employee in CLASSE, we have like 25 faculty and 50 like research associate and postdoc and probably roughly 100 students. But we also have over hundreds of technicians and outreach people and administrative people to make the organization running. Because the thing is like, we need people to build the accelerator. We need people to make the plant running. We need people to help us to convert the message to be deliverable. Because like a lot of time, I'm sorry to say, physicists we're talking gibberish, right? We're not really speaking English. But it's not that people are not smart enough to understand physics. It's just like we need to translate our language to make people understand what we're doing. And also like I think it is important for us to have the message to be clear, understood, so then people can think about what we could do to like how every of you can participate in physics. And I think I just want to really emphasize the physics, it's not just about the physicists. And there were so many it takes a village to make particle physics happen. And the last slide I want to point out is, if you are interested in learn more about particle physics, I would highly recommend you to follow our website and also follow us on the social media. We have so many interesting events happen all the time. And one of the events actually happened this Saturday. We have an open house at the Synchrotron Lab, so you can actually go down to the accelerator tunnel and see what's going on like by eye. And we will explain to you why do we install like a 200 frying pan in our $1 million accelerator. Please get please join us and follow us. And if you have any ideas, the best part of CLASSE and CHESS is it's funded by NSF, and there's a large grant that everyone can actually apply to use our really cutting edge like X resource to do your own study. If you have any biology thing, we also study plant and painting and all the different kind of way to use it. So you can write a proposal to the NSF and you can run this for free. So there's so many ways to get involved and take the advantage of our amazing facility on campus. So please stay in touch. And you can also feel free to find me after the movie if you have any question. But for now, without further ado, I think thank you so much for listening, and I hope you enjoy the movie. Thanks.